Buenas tardes. Quisiera primero dar una introducción en español y ya después voy a hablar en inglés. Bueno, quisiera darle la bienvenida a esta segunda parte de la sesión de Álgebra y Teoría de Números de esta 23ª edición del simposio del CIMAC. Hoy tenemos tres charlas en la sesión. La primera va a estar a cargo de David Krumm. La segunda va a estar a cargo de Juanita Duque. Y la tercera, que va a ser una charla plenaria, va a estar a cargo de Angela Robinson. I would like to thank everyone for being here today in this second part of the Algebra and Number Theory session of the 23rd edition of the CIMAC. Today, we're going to have three talks. The first one by David Krumm, the second one by Juanita Duque Rosero, and the third one is going to be a plenary talk, which is going to be delivered by Angela Robinson. First, I would like to introduce David. David is currently a visiting assistant professor at Reed College in Oregon, in the United States. David holds a bachelor's degree in mathematics from the University of Costa Rica and a doctoral degree from the University of Georgia. His main research interests are in the area of arithmetic dynamics, which applies tools from number theory and algebraic geometry to study various kinds of discrete dynamical systems. The title of today's talk from David is Classification of Periodic Portraits for Quadratic Polynomials over Quadratic Number Fields. So once again, thank you, David, and you may start.
All right, thank you. So let me just share my screen. Does that look good? Okay.
Perfect, yeah.
All right, so hello everybody, and many thanks to the organizers for inviting me to speak here today. So in this talk, I'll be discussing some ongoing joint work with John Doyle, and I'll begin with these pictures of directed graphs, which are taken from a 1998 paper by Bjorn Poonen. And so these figures represent what are known as pre-periodic portraits. And in this case, they correspond to quadratic polynomials with rational coefficients. So to explain precisely what's being depicted here, let me introduce a little bit of notation and terminology. So if K is a field and F is a polynomial with coefficients in K, I'll be writing Fn to denote the composition of F with itself n times. And an element alpha in K is called periodic under iteration of F if some iterate Fn fixes alpha. And in that case, the smallest such n is called the period of alpha. More generally, if there's some iterate Fm of alpha that is periodic, then alpha is called pre-periodic or eventually periodic. And perhaps I should point out that periodic points technically are also pre-periodic. So the term pre-periodic doesn't mean sort of strictly pre-periodic. And finally, the pre-periodic portrait, which is what we were seeing in the previous slide, I'll be denoting that by G of Fk, G for graph. And it's the directed graph, which has one vertex for each pre-periodic point of F. And for every such point, it has an edge from that point to its image. So it should be fairly clear that the image of a pre-periodic point is also pre-periodic, and therefore both alpha and F of alpha are vertices in that portrait. So for instance, if we choose just one example from the previous slide, we have this graph shown here. And so in this figure, the parameter C, which is in the top left corner of the square there, it represents the quadratic polynomial x squared plus c. So in this case, it's x squared minus 301 over 144. And the arrows in the figure represent evaluation of the polynomial. So if we evaluate at 23 twelfths, for instance, the output will be 19 twelfths. All right, so that's the meaning of those pictures that I showed. Now in the paper where this table of graphs appears, Poonen makes the following conjecture, which is well known in the field of arithmetic dynamics. And so it says that for every quadratic polynomial with rational coefficients, the portrait is isomorphic to one of the 12 graphs that we saw. So even though there are infinitely many quadratic polynomials, obviously, there seem to be only finitely many possibilities for what their portraits might look like. And in the same paper, Poonen showed that this conjecture would follow if it were known that these portraits for quadratic polynomials can never contain a cycle of length greater than 3. So the theorem is that if f is a quadratic polynomial with rational coefficients and its portrait doesn't have cycles of length greater than 3, then the portrait is isomorphic to one of those 12 graphs. And so the conjecture is now reduced to a question about possible cycle lengths. And all the current evidence does suggest that the cycle lengths of 1, 2, and 3 are the only possible lengths. So for instance, there's been a fairly extensive computer search carried out by Ben Hutz and Patrick Ingram. And all of their data supports this conjecture of only finding points of periods 1, 2, and 3. So at least for now, at the moment, it seems that Poonen's list of graphs is in fact complete. Although there's no proof of that yet, and in fact, it's not even known whether the complete list of graphs is finite, much less that it's just these 12 graphs. But in any case, if we were given any finite list of graphs that is supposed to be complete, the pigeonhole principle would force some of these graphs to appear infinitely often, since there are infinitely many quadratic polynomials and only finitely many graphs. So Poonen checked that indeed some of the 12 graphs in this table do seem to occur infinitely often. And this was proved later on by Xander Faber in 2015. So before I state Faber's theorem, let me just clarify one small point here, which is that every quadratic polynomial is equivalent in a dynamical sense to a polynomial of this form x squared plus c. So the term there is linear conjugacy. So any quadratic polynomial is conjugate by a linear polynomial to a map in this form x squared plus c. And I'll be denoting that by f sub c. And so if we're interested in studying the dynamical properties of quadratic polynomials, we can just restrict attention to maps of this simplified form. All right, so here's Faber's theorem, saying that among the graphs in Poonen's list, the ones that occur infinitely often, so the ones that occur as a portrait for infinitely many quadratic polynomials, are the ones that are marked here with a little blue triangle. The remaining ones obviously occur only finitely many times, but actually they're known to be unique. So the ones that are not marked with a blue triangle occur for a single parameter c. And well, you probably can't see the parameters in this figure, but each figure comes with the parameter that it comes from. So anyway, regardless of whether this table is complete or not, it is known which graphs in the table occur infinitely often. And then Faber went a little bit further by addressing the question of what might be missing from this table. So a second theorem of Faber, that a graph that is not in Poonen's list could only occur as a portrait for finitely many quadratic polynomials. So at least we know that Poonan's list, if it omits anything at all, which it probably doesn't, then it's only missing portraits that are very rare. And that's actually where things stand currently on this problem of classifying pre-periodic portraits for quadratic polynomials over the rationals. I think that's as far as anyone has gotten. So now the main focus of my talk today will be the corresponding situation over quadratic number fields. So we'll consider quadratic polynomials with coefficients in any quadratic field, and we'll ask similar questions. So what are all the possible portraits? Which of them occur infinitely often? For those that don't occur infinitely often, can we actually determine all instances of that graph? And what can we say about graphs that are currently unknown but might possibly exist? So that's what this talk will be about. But before jumping into that, I'd like to make a short detour to mention an analogy that motivates a lot of research in arithmetic dynamics. So it's a common philosophy in this area to think of pre-periodic points for a given map as being analogous to torsion points on an abelian variety. And this analogy often suggests theorems to prove in the dynamical setting by transporting them from the context of abelian varieties. And so a first example of this is a theorem of Northcott from a while ago. It says if K is a number field and F a polynomial over K of degree greater than 1, then it has a finite portrait over K. There are only finitely many pre-periodic points. So thinking of this analogy with torsion points, the corresponding theorem in the context of abelian varieties is that, well, for every abelian variety over a number field, the set of rational torsion points is finite. So this would follow, for instance, from the Mordell-Weil theorem. Okay, so these two results are considered to be analogous. And with this same analogy in mind, Joe Silverman and Patrick Morton made a conjecture in dynamics that corresponds to a well-known uniform boundedness conjecture for abelian varieties. So here are the two conjectures. The first one for abelian varieties. So this one says that, well, essentially, the number of torsion points on an abelian variety can be bounded in terms of the dimension of the variety and the degree of the ground field, but independent of the variety itself and of the particular number field. And the second one, the dynamical version, well, mainly says that the number of pre-periodic points of a map can be bounded in terms of the degree of the polynomial and the degree of the number field, but independent of the specific polynomial and the specific number field. And so in particular, in this Morton-Silverman conjecture, if we take n to be 1 and d to be 2, so that's basically the simplest case of the conjecture, the conjecture would imply that for quadratic polynomials over the rationals, there should exist only finitely many pre-periodic portraits because their size is bounded. It's probably that list of 12 portraits that we saw earlier, but in any case, it's expected to be a finite list. And in fact, the same would apply over quadratic number fields. So even though there are infinitely many quadratic number fields and infinitely many polynomials over those fields, the conjecture predicts only finitely many possible pre-periodic portraits for those maps. Well, so the current status of both of these conjectures is currently unresolved, but there has been significant progress made on both. So I'll just mention a couple of results. So there's a fairly recent theorem of Nicole Looper that says that the ABC conjecture implies the Morton-Silverman conjecture for maps of the form x to the d plus c. So conveniently, that includes the quadratic polynomials. And then in the case of abelian varieties, the conjecture was famously proved by Morel a while ago. And in the case of dimension 1, so in the case of elliptic curves. And so Morel's theorem stated here, there's a constant depending on the degree of a number field, such that every elliptic curve over a number field of degree d will have at most that constant number of preperiodic points. Oh, sorry, of torsion points. And so as a consequence of Morel's theorem, for number fields of a fixed degree, there should only be finitely many possibilities for what the torsion subgroup of the elliptic curve could be. Again, because the size of the group is bounded. And for small degrees, the possible torsion groups are actually known. And so here's Mazur's theorem over the rationals, which identifies for elliptic curves over Q, what are all the possible torsion subgroups that could appear. And so it says there are only 15 possible groups that are listed here. And in fact, each of these 15 groups occurs infinitely often as the torsion subgroup of an elliptic curve over Q. So thinking back to this analogy between torsion points and preperiodic points, Mazur's theorem here would be considered analogous to Poonan's conjecture, which gives us a complete list of all the possible portraits for quadratic polynomials over Q. And well, together with Faber's theorem that I also mentioned, identifying which of those portraits occur infinitely often. All right, so moving on to quadratic number fields, the complete list of torsion subgroups in that case is also known. And the question of which torsion groups occur infinitely often has also been worked out. So in this slide, I'm combining the work of several people. But basically what we have is a complete list of all the possible torsion subgroups. There are 26 possible groups, and they all occur infinitely often. So finally, that brings us to the main problem that I want to discuss today, which is to obtain a dynamical analog of the theorem in this slide. So in the case of quadratic polynomials over quadratic number fields, what are the possible preperiodic portraits? Which ones occur infinitely often? And all those questions that I mentioned earlier. Well, I don't know, maybe this might be a good time to answer questions if there are any. Is there anything I could clarify at this point?
I have a question,
Yeah.
David. When you were mentioning the theorem of Faber from 2015, where he identified some of these 12 graphs from Poonan's list that occurred infinitely often. I was wondering if some studies have been made about the frequency with which these tend to occur, like in some way, ordering polynomials, I don't know, by discriminant or some way, and if some of these graphs tend to occur like with a higher frequency than others, for example.
Yeah. So as far as I know, there's no results of that type, but I wouldn't be surprised if it's possible to prove something of that nature by using Faber's techniques. I'll actually have to keep that in mind. So part of what I'll be discussing today is a theorem similar to Faber's over quadratic number fields. And I'm thinking whether it's possible in that case to say anything
I mentioned this because I know there have been results in that direction in the context of these torsion subgroups for number fields. I mean, people have studied the frequency with in which some of these torsion subgroups appear for number fields. So it seems to me that maybe that would be in this analogy a similar question in spirit.
Yeah, it's a natural question. So I'll have to keep that in mind, but right now I don't know. I can't think of anything to say, but it would be interesting to try to prove some sort of bounds.
Thank you.
Any other questions? Okay, so around I think it was around 2011 or so that John Doyle and Xander Faber and I ran some computations to start gathering data on these portraits. And so this is what we came up with. There are 46 graphs here, and we found them essentially by choosing a large sample of quadratic polynomials over quadratic fields and computing their portraits. So there is an algorithm for computing the portrait of a given polynomial, and it involves finding all elements of bounded height in a given number field. And so at the time, there wasn't really a practical method for doing that. So part of the work that we had to do was come up with an algorithm for, given a specific number field and a specific height bound, list all the elements of the number field that meet that height bound, that don't exceed that height bound. But in any case, based on all the data we got, we made a conjecture similar to Poonan's conjecture that I mentioned earlier, stating that we expect these are all possible graphs. So for every quadratic polynomial over a quadratic field, the portrait should be isomorphic to one of the 46 graphs that we saw. And so going back to the table, you might notice that the cycle lengths that occur here are 1, 2, 3, 4, and 6. Right? There's a 6 cycle in one of them, but there's no 5 cycles or any cycle of length greater than 6. So we would like to prove a theorem similar to Poonan's theorem over the rationals, that under specific assumptions on cycle lengths, that our list of graphs is complete. Now, when we first gathered this data, we didn't really have much reason to believe that the list is complete. In fact, we very much had the reason to believe that it was not complete, because after running our computations, we discovered one new graph that we realized should exist. But the smallest example of it, once we ran a different search for just this specific one, the smallest example was just beyond the reach of the first computation. So our search didn't find it. So at that time, we weren't very confident that this was a complete list. But by now, it's become more clear by more recent work that we're probably not missing anything. So this is a problem that John Doyle worked on in his thesis, and combining John's results with some additional work that we did with Joe Wetherill, we were able to prove the second theorem in this slide. Suppose that the only quadratic points on certain curves, and I'll say more about those in a second. So suppose that the only quadratic points are the ones that are already known. Then if K is any quadratic number field and we have any quadratic polynomial over K whose cycle or whose portrait doesn't contain cycles of length 5 or greater than 6, then the portrait is in our list of 46 known portraits. So in other words, our list of graphs is complete modulo an assumption on cycle lengths and modulo an assumption about points on a few curves. So to explain that second part about the curves, in the context of elliptic curves, there's a well-known family of modular curves, often denoted x1 of n. And these parameterize elliptic curves with a torsion point of order n. And similarly, in the dynamical setting, for every graph in our table, let's call it G, there's a corresponding curve, x1 of G, which parameterizes quadratic polynomials having portrait isomorphic to G. And so in this theorem, we're referring to the modular curves for 4 of our graphs, which in our labeling scheme are labeled 10.3a, 10.3b, and so on. And well, so basically this slide summarizes our results up to this point. This is as far as we've gotten on the problem of determining all possible portraits. So there's this major assumption on cycle lengths. So it could very well happen that there's a portrait somewhere with a cycle of length 39 or something, and we just don't know about it. And we have no way of ruling that out at this point. And then there are still these few x1 of G curves to deal with. So for these 4 curves, we do have a list of points that's probably complete. And we have upper bounds on the number of quadratic points that they could have. But unfortunately, those bounds don't match the number of points that we've actually been able to find. And so there's still some work to be done there in either reducing those bounds or finding more instances of these graphs. All right, so moving on to another question I had mentioned earlier. Among the graphs that we did find, which ones occur infinitely often? So this is something that John and I have been working on more recently, and perhaps the main new result that I'll be mentioning today is that we've been able to answer that question. So the theorem is that among those graphs in the table, the ones that occur infinitely often are the ones that we've marked here with a little blue triangle. Now, the proof of that result has an easy part and a hard part. The easy part is deciding which graphs occur infinitely often as a subgraph of the portrait of some quadratic polynomial. The hard part, so that first part, let's call it the easy part, it mostly involves computing the genera of a few curves and citing Falting's theorem from Diophantine geometry. But then the hard part is showing that a given subgraph that occurs infinitely often is in fact the whole portrait, and not just part of something larger, of some larger graph that we didn't know about. So that's where all of the new ideas were required. Okay, so we know which graphs do occur infinitely often from the ones that we found. And as a complement to this theorem, we were also able to say something about graphs that we might be missing. So that's the second theorem in this slide. A graph that is not in our list of 46 graphs could only occur finitely many times as a portrait of a quadratic polynomial over a quadratic field. So it's just like the situation over the rationals. If we're missing any graphs, at least we're missing only things that are very rare. Okay, and that leaves us with one main question to address, which is regarding the graphs that occur only finitely many times. So the ones that are not marked with a blue triangle in this slide, can we determine all instances of those graphs? We know that they occur only finitely many times, so can we find all possibilities for a quadratic field and a quadratic polynomial over that field whose portrait looks like that? So you might remember from the beginning of the talk, for each portrait in Poonan's table, the table with 12 graphs, for each portrait that occurs finitely many times, we do know all instances of that graph. In fact, it's a unique graph, and we know precisely what is the unique instance of that graph. So the case over quadratic fields turns out to be much harder. The main issue is that there's only one field of rational numbers, but there are infinitely many quadratic fields, and that complicates things. But this is a project that John and I have occasionally continue to work on. And for most of the graphs, we have been able to determine all instances. And so the ones that we've managed to do are marked here with a check mark. So the blue ones are still the ones that occur infinitely often, and the ones with a check mark are the ones that occur finitely many times, and we know all instances of those graphs. So the overall strategy here is to, you pick a graph, look at the corresponding modular curve for that graph, and try to find all the quadratic points on those curves. And so that leaves really only a small number of graphs to deal with, and I'll single them out in this slide with a question mark. So for these few graphs, we think that we know all the quadratic points on their modular curves. But for various reasons, we can't prove that we know them all. And so just to give one example of what's the problem, what are the obstructions? So let's focus on one of these graphs, which is, in our labeling scheme, is called 10-2. So let's say that we wanted to determine all instances of this graph over a quadratic number field. Then that comes down to finding all the quadratic points on the curve whose equation is given here. It's a curve of genus 5. So we have to find all the solutions of that equation where x and z are either rational or both at least live in the same quadratic field. Now, with a little bit of work, you can reduce that problem to finding all the rational points on 4 hyperelliptic curves. I've given equations for 2 of them here, and they are curves of genus 3. And this is where we get stuck, because there are some standard Chabot-Coleman techniques that you can apply to this sort of question, and which we use all the time for all the other graphs. But that method requires a specific upper bound on the rank of the Jacobian of the curve. And these particular curves don't meet those bounds. So the method doesn't apply to them. So if I remember correctly, these curves, the Jacobian has rank 3, and the Coleman bound would be rank 2. So 3 is too big, which means we can't apply this technique. And so for now, we're a bit stuck here. But hopefully, as the methods for finding rational points on curves continue to be developed, this will become doable. Or maybe it's already doable and we just don't see how to do it. Well, I think I could probably pause for a second here and see if there are any questions before moving on.
I might have some questions, but maybe I'll leave them for the end of the talk.
Okay.
I have a question.
Yeah.
Is there anything like characterizing these modular curves in terms of like the genus, or like, so I'm assuming you already know the genus of all the modular curves. Is it something like a priori you should expect that it turns out to be that genus, or is just coming from what the graph is like?
Sorry, that we should expect to have which genus?
No, I mean, like, if there's like a bound on the genus that you can expect, like when you started with the work, or like if there are, you expect them to be like hyperelliptic or not.
Yeah, I mean, so I don't know of any very precise statement of the form, depending on the shape of your graph, the genus of the modular curve is going to be such and such. I don't know of anything like that, but there are some lower bounds that you can prove on the genus. And so very quickly, I mean, as long as your graph isn't almost trivial, the genus will be pretty big. These curves have fairly large genus usually. And so, yeah, unfortunately in my slides, I don't have any lower bound that I can just point to, but you can definitely prove lower bounds for these things. There's some work of Patrick Morton. There's a paper of Morton which gives an explicit formula for the genus in the case of a cycle. So if your graph is just a cycle, what is the genus of that modular curve? And based on that, you can compare, right? Since any pre-periodic point eventually lands in a cycle, you can compare the portrait of a cycle to the portrait, to a more general portrait. And by doing that, you can compare the genus of the cycle modular curve to the genus of a general modular curve. And so you can get lower bounds that way. But I don't know of any very precise formula for the genus in terms of the shape of the graph. Does that kind of answer your question?
Yeah.
Okay.
Thank you.
All right, so to start wrapping up the statements of results, I'll mention a new type of question that doesn't really come up over the rationals, which is, if we look at our table of graphs and consider the graphs that do occur infinitely often, what can we say about the number fields over which they occur? Could it be any quadratic field? So in particular, does the existence of a specific graph over a particular field, does that have implications for standard invariance of the number field, like discriminant, class number, and things like that? So I'll mention a couple of results that we were able to obtain in that direction. The first one is for the graph that we call 10, 3, 1, 1, that's shown here. If in any number field where that graph does occur as a portrait, the prime 2 has to split and 3 cannot be inert. So that's a statement about the splitting of primes, and which of course you could translate into something about the discriminant. And the next one is about class groups. So for each okay, I should be careful. The theorem is that there are infinitely many imaginary quadratic fields where this portrait, this 4 cycle, does occur, and the class group has an element of order 10. Now, that's what we can currently prove, but what really seems to be true is that for every imaginary quadratic field over which this portrait occurs, the class group has an element of order 10, with one known exception. And we're just still working on trying to understand the exceptions. But it's probably every such imaginary quadratic field with one exception. So there are implications when a specific graph occurs over a field. Typically, there are implications for standard invariance of that field. So I'm giving just 2 examples here, but you could certainly prove similar statements for other graphs. Let's see, how are we doing with time? Yeah, okay, so I'll mention that incidentally, as I was thinking about this kind of question years ago, one kind of unexpected new result popped out, which has to do not with these dynamical modular curves, but with the classical ones for elliptic curves that parameterize elliptic curves with a torsion point of given order. So I'll mention one such result. So this one says that if you have an elliptic curve over a quadratic number field, and it has a torsion point of order 13, which can certainly occur, then in that field, 2 has to split and 3 is unramified. And then there were similar results for points of order 16 and points of order 18. And this is something that I actually don't quite understand yet. So this was a pretty amazing coincidence that this theorem, which I arrived at by thinking about pre-periodic points, it turned out to imply a conjecture that Dino Lorenzini had made about Tamagawa numbers of elliptic curves. So there's some interesting connection here with elliptic curves, but at this point, it's not quite clear to me why that would be. So I think it's a little bit more than an analogy between torsion points on, on elliptic curves and pre-periodic points. But making that precise, I currently don't know how to do. Okay, so I'll start wrapping up by walking through the steps or the main steps in the proof of one of our results, just to give a sense for what sorts of ideas are involved. So let's see, for instance, why this graph, 10(3b), why that graph occurs only finitely many times over quadratic fields. So this is one of the graphs that had a question mark in that earlier slide. Okay, so what we want to prove here is that the modular curve for this graph has only finitely many points defined over quadratic fields. And so the first observation to make is that this graph contains another one of our graphs, which is called 8(3). And it's the second graph here in the slide. And you can easily compute equations for the corresponding modular curves for these graphs, and you can compute the genus of each one of them. And it turns out to be 9 for the graph, for the bigger graph, and 2 for the smaller graph. All right, so knowing that, here's the argument. Let's call, I guess I had already said, let G be the graph 10(3b) and H be its subgraph. So then the inclusion of H into G is going to give a dominant map of curves in the opposite direction, from x1 of G to x1 of H. So this x1 construction is actually functorial, and it's contravariant. So a map from H to G gives you a map from x1 of G to x1 of H. And now the proof proceeds by contradiction. So let's suppose that actually x1 of G has infinitely many quadratic points. Well, there's a theorem of Harris and Silverman in Diophantine geometry. This in principle has nothing to do with dynamics. It's just a theorem about curves that have infinitely many quadratic points. And it turns out there aren't too many ways of having infinitely many quadratic points. The curve has to be either rational or hyperelliptic or bielliptic, meaning it has a map of degree 2 onto an elliptic curve. So the theorem of Harris and Silverman says there would have to be a map of degree 2 from x1 of G onto some curve of genus 0 or 1. So now we actually have maps from x1 of G onto 2 different curves, right? There's a map onto x1 of H, and there's a map onto this curve C of genus 0 or 1. And there's this inequality of Castelnuovo and Severi, which applies precisely in that context when you have 2 maps that are sort of independent out of the same curve. And what it gives you is an upper bound for the genus of that curve. And so applying that inequality, we would get that the genus of x1 of G, just plugging things into the inequality, it would be twice the genus of the curve C plus twice the genus of x1 of H. And well, the genus of C was at most 1, and the genus of x1 of H we knew was 2. So this upper bound turns out to be 7, and that contradicts the fact that we know the genus of x1 of G, which is 9. And so that argument shows there could only be finitely many quadratic points on x1 of G, and therefore only finitely many instances of a quadratic polynomial over a quadratic field whose portrait looks like this graph 10(3b). And let's see, so I should mention so this argument just shows the finiteness, right? It doesn't, there's still the problem of finding all those finitely many instances, which we haven't been able to do. So that part is still very much open. But at least we know there's finitely many. Okay, well, I think actually that's all I had to say today. So I'll stop here, and thanks to all of you for your attention.
Thank you very much, David, for your talk.
Thank you.
Are there any questions for David? I have a question, but I'll let the other people ask. No? Then I'll ask my questions. Actually, one of the questions I had, you sort of answered later on in your talk. My question was if there was some relation between the arithmetic of the quadratic fields and what was happening at the level of the graphs of the associated to the polynomials. But maybe with regards to that, I was just wondering if you guys looked at, for example, what happened if you restricted only your fields to, say, real quadratic. Do all of the graphs in your list with the blue triangle occur? And what happens similarly if you restricted, for example, only to imaginary quadratic fields? Does that still happen, or are some of them missing? Just...
Yeah, we definitely looked into that. Now, let me try to remember where we did that. Yeah, so there's a paper that I wrote with John Doyle and Xander Faber a while ago, and in that paper we do address this question. I don't remember the precise results, but some of the graphs we can prove, occur only over real quadratic fields or only over imaginary fields, or we can prove that in fact there are infinitely many instances over both real fields and imaginary, for example. So there are results of that type, but I'd have to look up. It's been a while, actually. I don't remember the exact results, but they are there.
Okay.
Yeah.
And I was wondering, I mean, does something similar happen if maybe you look, for example, you restrict the class number only? Like, say you're going to look at number fields, say imaginary or quadratic of a given class number. I mean, you might not have looked into that. I was just wondering.
Yeah, that's actually one of the things that I'm perhaps most interested in continuing to think about. So let's see if I can go back to the class number theorem. So yeah, the second theorem here. I'm kind of annoyed that we can't prove that this is always the case. There is, if you just explore this computationally, it really seems that there's one exception to this statement, that every time you see this graph over an imaginary quadratic field, the class group has an element of order 10. So that it turns out to be more subtle than I expected initially, but that's kind of the one direction that I would really like to continue to explore. And unfortunately, at this point, I really don't have much to say beyond the statement here in the slide. There should be there should be some sort of statement of the form. Well, I guess the main issue is we need to understand the Jacobians of these modular curves a lot better. So I suspect that by understanding the torsion points on those Jacobians, that the reason that there's an element of order 10 in these class groups is that the Jacobian has a torsion point of order 10, which should in some sense specialize to an element of order 10 in the class group. But making that connection quite precise and actually dealing with the the possible reduction types of those Jacobians is the hard part. And I think currently there's very little known about the Jacobians of these modular curves. So there's plenty of work to be done there.
I see. Thank you. And one final question for me. This is related more to this sort of analogy you were making between the dynamical world and the world of elliptic curves, for example. I don't know if there are, for example, either zeta functions or L functions related to these objects, and if there are, for example, conjectures about you know, possible the arithmetic behavior of the objects in relation to the analytic properties of these objects, if there are.
Yeah, I only know of one paper that addresses that, which is obviously a very natural question. And I haven't really kept up on the literature in that direction. So I don't know if there's anything very recent. And I'm trying to remember which paper it was, but it's kind of a paper from the 90s, and I don't know if anyone has continued to think about that. But yeah, there should be zeta functions associated to these things, and it could certainly be helpful to look into them. But yeah, I don't know. I don't know of anything recent or I don't know of anyone who's currently working on that either.
Are there any more questions for David?
Yeah, I have a question.
Sure.
So I was wondering if you have some idea of the heuristics of how often these graphs appear, the graphs that appear infinitely many often.
How often they appear?
Yeah.
Yeah, no, I don't. I think this is, Adrián had asked about this earlier, I think. And no, I don't think I know of any results of that type, but you know, someone should work it out. Yeah.
Any more questions for David? Okay, well, if not, then let's thank David again for the wonderful talk.
All right, thanks everyone.
So it's 2:52 here. So the next talk should begin in about 7 minutes. So I think we can take a short break and return here at 7 minutes.